Hi everyone, my name is Houssam Matbouli. I'm a master's student at the Department of Mechanical Engineering at the Catholic University of Leuven, Belgium. And my co-author is Iyad Faysal. He's an assistant professor at the Department of Mechanical and Mechatronics Engineering at Rafik Hariri University, Lebanon. And today for the FEDSM 2020 conference, I would like to present to you the performance assessment of a NACA 2412 surrogate model using the non-intrusive polynomial chaos method. One major component that allows planes to fly is its wing, or what is known by the airfoil. When a flow goes over an airfoil at its cross-sectional surface, the pressure and shear profiles can be determined. The projection of these vectors on the vertical direction will yield the lift force that should exceed the gravitational force in order to keep the airplane in the air. On the other hand, the projection of these vectors on the horizontal direction will yield the drag force that opposes the motion of the plane. The sum of the lift and drag vectors will simply yield the resultant vector. The concept of lift and drag is used in several real-life applications, like drones with propellers, helicopters with rotary blades, flapping robots for civil and defense applications, and wind turbines for renewable energy applications. Research studies were conducted on airfoils to increase the lift force it can generate and reduce the drag one. By doing so, the fuel consumption of airplane decreases, which can have a huge impact on the carbon dioxide emission of the aviation industry. One technique treats the detachment of the flow from the baseline airfoil surface, which can suddenly stop lifted generation. The airfoil is modified to a co-flow jet airfoil where the flow is sucked downstream and pumped back upstream, creating a flow loop that avoids detachment. Another technique called turbulence control is done by vibrating the rear edge of the airfoil to decrease turbulence downstream and thus drag forces. A third one proposed by NASA is a deformable airfoil that can change its shape based on the aircraft speed in order to maximize lifted generation. However, designing such systems is complex and requires several prototypes. Physical prototypes are costly and time-consuming, which is why we need to use numerical simulations first to reduce the number of physical models. In this paper, we want to model the flow over a NACA 2412 airfoil which is installed inside a wind tunnel prototype. This was done with the help of the finite volume method, and further computational cost reduction was achieved through the development of surrogate models. The surrogate models can compute the coefficient of lift in a fraction of seconds and can have different orders, leading to a compromise between computational cost and accuracy. Looking at the methodology applied in this research, the experimental results were first extracted from the prototype. A CFD model was built and validated. Then several surrogate models were built in an iterative process, starting with an initial order of 2, and then we carried the analysis for different orders k. Finally, a performance analysis is done on all the built surrogate models with different orders in order to deduce the optimal one. Looking first at the experimental procedure, 14 pressure sensors are mounted on different locations of the airfoil, and there are simply tubes connected to manometers so that when there is a flow over the airfoil, the red fluid level varies accordingly. In addition, a pitot-static tube is inserted next to the inlet and allows us to read the static and total pressure. Afterwards, these pressure values are plugged in an equation provided by the wind tunnel manufacturer in order to deduce the velocity of the flow, and therefore the Reynolds number. From the 3D view of a flow over an airfoil, we can look at the cross-sectional surface with pressure and shear force vectors. From the measured experimental pressure values, the drag and lift force are calculated using the displayed formula. However, the shear term is neglected due to the difficulties involved in measuring the shear force. Afterwards, using the calculated lift and drag force values, the lift and drag coefficients are calculated accordingly. Now that the experimental coefficient of lift and drag were calculated, we can proceed with building the CFD model. Describing the flow behavior is done using the Navier-Stokes equation, which are made of the continuity and momentum balance. discretizing these equations by first applying the divergence theorem, then using a linear interpolation for diffusive terms and the second-order upwind scheme for the convective terms, will result in one that relates each cell center with its neighboring cells along with a source term. Then, a simple algorithm that couples the pressure and velocity is applied by using the pressure correction P', then iteratively solving until convergence is reached. Afterwards, the flow field should be computed for different flow regimes and angle of attacks. Then, the coefficient of lift and drag can simply be calculated using the same formulas presented in previous slides. Now that the coefficient of lift and drag of both experimental and CFD models are determined, the two can be compared in order to check the validity of the CFD model. Looking at the coefficient of lift at a Reynolds number of 5575.73 for all angle of attacks of both CFD and experimental results, one can deduce that the two curves have similar behavior, and therefore the CFD model is deemed accurate. Now that the CFD model is validated, it can be used to generate additional sets of data that will be later fed to the surrogate model. But first, the technique to construct the surrogate model will be presented. There are two main polynomial chaos techniques used to build the surrogate model. The first one being intrusive, as it modifies the Navier-Stokes equation, and another one being non-intrusive, since it treats the system as a black box and do not modify the Navier-Stokes equations. The non-intrusive one is found to be less complex and less time-consuming, which is why it will be employed in this paper. The non-intrusive polynomial chaos expansion, or NIPC technique, expresses a set of response values R of a random variable input vector xi as the sum of the polynomial chaos coefficients alpha j multiplied with a random basis function psi. In this paper, the random variable input vector xi1 is the angle of attack vector, the random variable input vector xi2 is the Reynolds number vector, and the response value vector r is the coefficient of lift vector. The random basis function is dependent on the input vectors that are the Reynolds number and angle of attacks and is therefore known. This leaves us with the only unknown in the equation being the polynomial chaos coefficients, and deducing such coefficients allow us to input any combination of Reynolds number and angle of attack and get the coefficient of lift. The random basis function psi can be univariate or one-dimensional when having one random input vector, and multivariate or multidimensional when having two or more random input vectors. The random basis function differs based on the uncertainty distribution of the input data, and using a normal distribution in this paper for the input data, the Hermite polynomial is chosen, and its general formula is displayed along with the Hermite functions up to order 6. One way to calculate the multivariate random basis function psi is to multiply the univariate ones with a certain ordering. So if we have a random input vector xi1 with 4 angle of attack values, and a random input vector xi2 with 3 Reynolds number values, and if we express the univariate random basis as psi kn, with k being the component index and n the input vector index, one can deduce the univariate random basis function vectors b, and a full permutation of these vectors lead to the matrix A. From matrix A, a reverse lexicographical ordering is implemented by comparing each two indices. If an index 20 is larger than the other one 01, it is directly ordered higher. If two indices are equal, their difference is first calculated, and if the leftmost non-zero entry, which is -1 in this case, is negative, the first term, 1, 2, is ordered higher than the second one, 2, 1. In addition, truncation of matrix A is possible in order to achieve a certain number of expanded terms nt. In this case, removing the last row and column expands the psi until the fifth term. Going back to the initial NIPC formula, where the set of response of the random input variable vector was expressed as the sum of the polynomial chaos coefficients multiplied with the random basis function, it is possible to expand the equation with the multivariate basis functions, and then introduce the combination of univariate ones. In this formula, P is the order of univariate basis of input vector xi1, R is the order of univariate basis of input vector xi2, and since the two are multiplied, their summation is equal to k, the order of the polynomial chaos expansion. Afterwards, the index notation of the random basis is left out. Then, if we introduce the angle of attack vector with n components, and Reynolds number vector with m components, we can generate n times m datasets. Each pair of angle of attack and Reynolds number corresponds to a value of coefficient of lift. Inserting the set of data in the expanded equation yields a system of equations that can be expressed in a matrix form. The coefficient of lift vector CL is equal to random basis matrix A multiplied with the unknown coefficients vector alpha. It is worth noting that matrix A has relatively large numbers, and the direct inversion will lead to a badly conditioned matrix. Therefore, a preconditioning technique is used to enhance the matrix condition. Also, if the polynomial chaos coefficient vector expansion is less than the total expansion NT, least squared method is employed to approximate the solution. The final step is to prepare the data that needs to be fed to the model. The required number of data sets to achieve an acceptable accuracy is defined by the displayed formula taken from previous literature. In addition, an oversampling ratio is introduced to increase the minimum sample data limit by a certain factor. In our case, the angle of attack varies from -60 to 60 degrees with increments of 5 degrees, leading to a total of 17 angle of attack values. The Reynolds number varies from 5,000 to 13,000 with increments of 500, leading to a total of 25 Reynolds number values. Therefore, the coefficient of lift will have a total of 425 values, and knowing that only two input vectors are used, the formula above relates the order k to the OSR. Now that the surrogate model has been built, results for different orders are generated and will be presented. For compactness, three different orders will be shown, 12, 26, and 48, for the same Reynolds number of 6,500 for all angle of attacks. A surrogate model of order 12 has small discrepancies with the CFD model, mainly around the angle of attack of 0. On the other hand, a surrogate model of order 26 has little to no discrepancies with the CFD model results for all angle of attacks. However, for the order of 48, a large divergence is noticed at some extreme locations of the angle of attack, leading to unphysical CL values up to 50. Therefore, increasing the order does not necessarily mean that the solution will be more accurate. In order to deduce the optimal order, the coefficient of lift of all the generated surrogate models with different orders k have to be compared with the CFD one. For compactness, the results will only be shown for two sets of Reynolds numbers and angle of attack. In both cases, the order 26 achieved the best accuracy, and in the case of Reynolds number equal 12,500 and angle of attack equal 58, higher orders above 38 diverged to unphysical coefficient of lift values. As a conclusion, a CFD model of the NACA 2412 airfoil was built from an experimental prototype and validated. Datasets generated from the CFD model were used to construct a surrogate model with different orders k. By comparing the results of the CFD and different surrogate models, an optimal order was found, and divergence from this optimal order decreased the model accuracy and might even lead to unphysical values. As a future work, the geometrical parameters defining the NACA 2412 airfoil, like the camber line and thickness, could be included. This would allow us to see the effect of any geometrical change on the coefficient of lift, leading to the airfoil shape optimization. Also, an intrusive surrogate model could be built and compared with the NIPC in terms of accuracy and computational cost. Finally, I would like to thank you for your time and attention.